Okay, this is part 3 of our fluids, and we're going to look at first some early hydraulic uses. Here we see a water wheel, and this would provide flowing water would be flowing along here or up here, goes over the wheel, which turns the wheel and causes this to turn and create rotational motion. And it was often used to then inside here to move a mill that would grind some kind of grain through a series of some gears. We also have ancient aqueducts used to transport water. They were gravity fed from up in the mountains, and they were used for practical purposes and decorative. Today we have hydraulic systems in all sorts of places where the fluid's in motion, and for instance on a turbine, as the water flows by, it spins the turbine to create energy. We also use hydraulic power in many applications. For instance, here on this fire truck, we can see the hydraulic cylinders here on the stabilizers, or here to raise the ladder up. Here's another system where we can see the hydraulic cylinders and pistons here and here. The fluid inside it is pressurized, and fluid does not flow quickly or continuously. The force is transmitted by pressure. We saw in our last section that pressure equals force divided by area. And these are most common in industrial settings as compared to, say, commercial or residential. Now, comparing hydraulics, which is liquid, to pneumatics, which is gas, we see a number of comparisons here. The liquids, less compressible, so they're smoother and slower motions, but they're generally more precise and we get more power out of them. They do operate at lower pressures. However, because it is a liquid and not a gas, if we do have a leak, you're going to have some cleanup. For instance, if you have a hydraulic fluid leak, it's going to actually cause dripping and pooling of the fluid. However, it is naturally lubricated as compared to when we're using pneumatics with gases, where you have to add some extra kind of lubricant. So one of the concepts with liquids is flow rate, and there's two different things we're going to talk about. The flow rate, which is the volume of liquid going down a system, versus the velocity, which is the speed that the liquid's moving. And these two are related through the cross-sectional area here. So take a minute and look at the symbol for flow rate is Q, and what units you would use here. Notice is gallons per minute, feet per second for velocity, and then area. And here's our formula. The volume we have is equal to the velocity times the area. Check the units and see if those units make sense to you. So for instance, here we have a problem that we're going to do. We have a flow rate Q in 15 gallons per minute, and the line has an inside diameter of 2 inches. So we would need to, they want us to find the velocity. So what we're missing here, we've got Q and we've got V, but we need A for our formula. So first they're going to convert over to inches cubed in our Q, so that this is in the same units as our diameter. You'll need to write this conversion down so that you have it to use on your problems. And they do a simple conversion with a conversion factor like you learned in IED. And they've converted over Q from this to this. Here's our new Q. We still need to plug our diameter in to find the area. Remember, this is diameter, not radius. And now we can finally plug in our Q and our A here to find the volume. Be sure to work along and make sure that you know how to get to this answer. The other idea that we're going to look at in this section is mechanical advantage. Remember that from Simple Machines? It's force at the output over force at the input. For instance, a small force here and a big force there. Not sure this one would work, but that's what their picture is. Write this formula down so you have it when we move on. This is what a real system would look like. Maybe a smaller cylinder here where we push down to raise a bigger cylinder here. And here we have 100 pounds applied to the input, so we have force in, but we don't know the force out. So how would we find that? So I've just rewritten these same problems here. And they first say we need to find the area of both cylinders if we know the radius of each one. So they're going to just use the areas. And notice they're being careful of which one is an input and an output in each case. So we now have the area of the small one and the area of the big one. They now want us to find the pressure in the system. Because it's a closed system, it's going to have the same pressure everywhere. So I can use pressure equals force divided by area to find the pressure here. And then the pressure here is the same. Notice that's these right here to find the pressure. So now we know the pressure in the entire system, so now we're going to find the force out. Pressure equals force divided by area. Plug in and solve to get 900 pounds on our force out. So for the mechanical advantage, it's just going to be force out divided by force in, giving us a mechanical advantage of 9. That's it for part 2.